Understanding ownership. Ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we will talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. Ownership is Rust's most unique feature. Has a deep implication for the rest of the language. It enables Rust to make memory safety guarantees. It enables Rust to make memory safety guarantees. It enables Rust to make memory safety guarantees without needing a garbage collector. So ownership makes Rust doesn't need a garbage collector. Okay. Borrowing slices and how usually set up. So what is ownership? Ownership is a set of rules that governs how a Rust program manages memory. Ownership is a set of rules that governs how a Rust program manages memory. All programs have to manage the way they use the computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. Ownership is a set of rules that governs how a Rust program manages memory. Ownership is a set of rules. Ownership is a set of rules that governs how a Rust program manages memory. Ownership is a set of rules that governs how a Rust program manages memory. Ownership is a set of rules. Ownership is a set of rules that governs how a Rust program manages. Okay. So it's a set of rules. Okay. So all programs have to manage the way they use computer's memory while running. All programs have to manage the way they use computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. The programmer must explicitly allocate and free the memory. The programmer must explicitly allocate. The programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. Memory is managed through a system of ownership with a set of rules. Rules that the compiler checks. Okay, so compiler checks some rules to manage the memory. That is the old approach. If any of the rules are violated, If any of the rules are violated, the program won't compile. If any of the rules are violated, the program won't compile. Okay, none of the features of ownership will slow down. None of the features of ownership will slow down your program while it's running. None of the features of ownership will slow down your program. Okay, so it doesn't affect any kind of performance issue. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you will find it to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you will have a solid foundation for understanding the features that make Rust unique. You will have a solid foundation for understanding the features that make Rust unique. In this chapter, you will learn ownership by working through some examples that focus on a very common data structure, strings. Solid foundation of understanding features that also in this chapter, you will learn ownership by working through some examples that focus on a very common data structure, strings. So I'm going to learn ownership with data type string. Okay. The stack and the heap. Many programming languages don't require you to think about the stack and the heap very often. But in system programming language like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. The parts of ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime. Parts of ownership will be described. The parts of ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. Both the stack and heap are parts of memory available to your code to use at runtime. Wait a second, let me check. Many programming languages don't require the okay, yes. But in a system programming language like Rust, whether a value is on the stack or the heap affects that. But in the systems programming language like Rust, whether a value is on the stack or the heap affects how the unique what? Whether a value is on the stack. But in a system programming language like Rust, whether a value is on the stack. Whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. But in you better what does this mean? Like whether a value is on the stack or the heap affects how the language behaves. Affects how the language behaves and why you have to make certain decisions. Oh. Parts of ownership will be described in relation to the stack and the heap later in this chapter. Okay, so here is a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime. Both the stack and the heap are parts of memory. Both the stack and the heap are parts of memory. Both the stack and the heap are parts of memory, yes. So available to your code to use at runtime. Both the stack and the heap are parts of memory available to your code to use at runtime. but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in first out. Think of a stack of plates. They are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack, and removing data is called popping off the stack. All data stored on the stack must have a known, fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. So it's second of some place in per file. The heap is less organized. When you put data on the heap, you request a certain amount of space. The heap is less organized. The heap is less organized. When you put data on the heap, you request a certain amount of space. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer. Memory allocator finds, okay, so which is the address of the location. This process is called allocating on the heap. And is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating. Okay. This process is called allocating on the heap and is sometimes abbreviated as just allocating. That's very interesting, okay. Because the pointer to the heap is known, fixed size, you can store the pointer on the stack, but when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. Pushing to the stack is faster than allocating on the heap. Pushing to the stack is faster than allocating on the heap. Because the allocator never has to search for a place to store new data, that location is always at the top of the stack. Comparatively, allocating space on the heap requires more work. Allocating space on the heap requires more work because the allocator must first find the big enough space to hold the data and then perform bookkeeping to prepare for the next location. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Wait a second. If someone in your group comes late, they can ask where you've been seated. Okay. Okay, yeah, faster. Yes. So comparatively allocating space on the heap requires more work, yes, because once we find the first one big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack, because you have to follow a pointer to get there. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Contemporary. Continuing the analogy, consider a serve at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving to the next table. Wait a second. Accessing data in the heap is slower than accessing data on the stack, because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Accessing data in the heap is slower than accessing data on the stack, because you have to follow a pointer to get there, yes. Contemporary processors are faster if they jump around less in memory. What does it mean? So, continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table. It's most efficient. It's most efficient to get all the orders. It's most efficient to get all the orders. It's most efficient to get all the orders at one table before moving on to the next table. It's most efficient to get all the orders. It's most efficient to get all the orders at one table. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from the table A, taking an order from table A, then an order from table B, then on one from A again. And then one from B again would be a much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, as it's on the stack, rather than farther away, as it can be on the heap. Yes, that makes sense. When your code calls a function, that value is passed into the function. When your code calls a function, when you call function, the values passed into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. When your code calls a function, that values passed into the function, including potentially pointers to data on the heap. When your code calls a function, that values passed into the function, including potentially pointers to data on the heap. Oh, what? When your code calls a function, the values passed into the function. Okay, yeah, including potentially pointers to data on the heap. And the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Yeah, makes sense. Keeping track. But why does it say this? Keeping track of what parts of a code are used, what data on the heap, minimizing the amount of the duplicate data on the heap. Minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. Keeping track of what parts of code are using what data on the heap. Minimizing the amount of duplicate data on the heap. And cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that the main purpose of ownership is to manage heap data and can help main purpose of ownership is to manage heap data. Can help explain why it works the way it does. Ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. First, let's take a look at the ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the example that illustrate them. Each value in Rust has one owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Ownership rules. First, let's take a look at the ownership rules. First, let's take a look at the ownership rules. First, let's take a look. Okay. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has an owner. Each value in Rust has an owner. Okay, there can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Variable scope. Now that we are past basic Rust syntax, we won't include all the env fn main function main code in examples. So if you are following along, make sure to put the following examples inside the main function manually as a result. Our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. As a first example of ownership, we will look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following variable. As a first example of ownership, we will look at the scope of some variable. A scope is the range. within a program for which an item is valid. Take the following variable. So the variable s refers to the string literal. Wait a second. Scope is. Let s allow. The variable s refers to a string literal. The variable s refers to a string literal. The variable s refers to a string literal where the value of the string is hard-coded into the text of our program. The variable s refers to a string literal where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. Listing 4-1 shows a program with comments annotating where the variable s should be valid. The variable s refers to a string literal where the value of the string is hard-coded into the text of our program. The variable s refers to string literal where the value of a string is hard-coded into the text of our program. Where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. Listing 4-1 shows a program with comments annotating where the variable s should be valid. Let s allow. S is not valid here, it's not yet declared. S is valid from this point forward. To stop with S, this scope is now over, and this is no longer valid. Range is a program which an item is valid. A variable and the scope in which it's valid. In other words, there are two important points in time here. When S comes into scope, it is valid. When S comes into scope, it is valid. It is valid. When S comes into scope, it is valid. When S comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to that to other programming languages. Now we will build on top of this understanding by introducing the string type. The string type to illustrate the rules of ownership. We need a data type that is more complex than all those we covered in the data types. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types section of chapter 3. The types covered previously are all known size, can be stored on the stack and popped off the stack when their scope is over, and can be quickly and trivially copied to make a new independent instance if another parse Boolean trivially copied to make a new independent instance if another part of code needs to use the same value in a different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up the data, and the string type is a great example. We will concentrate on the parts of a string that are related to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We will discuss string in more depth in Chapter 8. We will concentrate on the parts of a string that relate to ownership. These aspects also apply These aspects also apply to other complex data types. Whether they are provided by the standard library or created by you, we will discuss string in more depth in Chapter 8. We've already seen string literals, where string value is hard-coded into our program. We've already seen string literals where a string value is hard-coded into our program. We've already seen string literals. We've already seen string literals. We've already seen string literals, okay. Where a string value is hard-coded into our program. Where a string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they are immutable. Another is that not every string value can be known when we write our code. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For those situations, Rust has a second string type, string. This type manages data located on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literals using the form function like so. This type manages data located on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function. What? Another is that not every string value can be known when we write our code. String value can be known when we write our code. For example, what if we want to take user input and for these situations, Rust has a second string type string. This type manages data located on the heap and as such is able to store an amount of text that is unknown to us at compile time. And as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. You can create a string from string literals. Yes. The double colon operator allows us to namespace this particular from function under the string type rather than using some sort of name like a string from We will discuss this syntax more in the method syntax section of chapter 5, and when we talk about namespacing with modules in passage for referring to an item in the module 3 in chapter 7. This kind of string can be mutated. Let mut s equals string from hello. S.push underscore str. Push underscore str. Must append a literal to a string. Let mut s equals to string from hello. S push s dot push underscore str. S dot push underscore str. Push str append the return to a string. This will print hello world. So what's the difference here? Why can string be mutated but returns cannot? The difference is how these two types deal with memory and allocation. In the case of a string literal, we know that what contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient. But these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time. We can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time, when whose size might change while running the program, with the string type in order to support a mutable global piece of text. With the string type in order to support a mutable global piece of text, we need to allocate an amount of memory on the heap, unknown at compile time, to hold the contents. But these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary. For each piece of text whose size is unknown at compile time, and whose size might change while running the program. With the string type, in order to support a mutable global piece of text, we need to allocate an amount of memory on the heap, unknown at compile time, to hold the contents. This means the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with our string. With the string type, in order to support the mutable global piece of text, we need to allocate an amount of memory on the heap. We need to allocate an amount of memory on the heap unknown at compile time to hold this from the contents. This means the memory must be requested from the memory allocator at runtime. The memory must be requested from the memory allocator at runtime. We need a way of returning this memory of the allocator when we are done with our string. We need a way of returning this memory. We need a way of returning this memory to the allocator. We need a way of returning this memory to the allocator when we are done with our string. We need a way of returning this memory to the allocator when we are done with our string. We need a way of returning this memory. We need a way of returning this memory to the allocator. We need a way of returning this memory to the allocator. Yes. When we are done with our string, okay? So the memory must be requested from the memory allocator at runtime. The first part is done by us. when we call string from, its implementation requests memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with a garbage collector, the GC keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a GC, it's our responsibility to identify when memory is no longer being used and call code to explicitly free it, just as we did to recast it. Doing this correctly has historically been a difficult problem. If we forget, we will waste memory. If we do it too early, we will have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4-1 using a string instead of a string literal. However, the second part is different. In languages, garbage collectors cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without the GC, it's our responsibility to identify when memory is no longer being used and call code to explicitly free it, just as we did to recast it. Doing this correctly had historically been a difficult programming problem. Doing this correctly has historically been a difficult problem. Yep. If we forget, we will waste memory. If we do it too early, we will have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. However, the second part is different. Second part. In languages with garbage collector, yes, anymore. And we don't need to think about it. In most languages without GC, it's our responsibility to identify when memory is no longer being used and call code to explicitly free it, just as we did to recast it. Doing this correctly has historically been a difficult programming problem. If we forget, we will waste memory. If we do it too early, we will have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4-1 using a string instead of a string literal. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of the scope. The memory is automatically returned once the variable that owns it goes out of scope. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4-1 using a string instead of a string literal. S is valid from this point forward. Do stuff with S. This scope is now over, and S is no longer valid. There is a natural point at which we can return the memory our string needs to the allocator. There is a natural point. There is a natural point at which we can return the memory our string needs to the allocator. Let me see. There is a natural point. There is a natural point at which we can return the memory our string needs to the allocator. There is a natural point. There is a natural point. There is a natural point at which we can return the memory our string needs to the allocator. There is a natural point at which we can what? Okay, so we can return the memory, which we can return the memory of our which we can return the memory our string needs to the allocator. Which there is a natural point at which we can return the memory our string needs to the allocator. And return the memory our string needs. When S goes out of scope. There's a natural point at which we can return the memory our string needs. Return the memory our string needs to the allocator when S goes out of scope and a variable goes out of scope. When S goes out of scope and a variable goes out of scope. Rust calls a special function for us. This function is called drop, and it's where author of a string can put the code to return the memory. And it's where the author of a string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. The function is called drop, and it's where the author of a star string can put the code to return the memory. It's where the author of a string can put the code to return the memory. Rust calls the drop automatically at the closing curly bracket. Rust calls drop automatically at the closing curly bracket. Rust calls drop automatically at the closing curly bracket. Rust calls drop automatically at the closing curly. Okay, but what does this mean? This function is called drop, and it's where other author of string can put the code to return the memory. Author of string can put the code. Just for the okay. What the? Oh my god, so long. Oh, it's not easy, really. In C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition. It's initialization. What? In C++, this pattern of deallocating resources at the end of an item's lifetime, sometimes called resource acquisition, is initialization. The drop function in Rust will be familiar to you if you've used the array2 patterns. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of a code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's explore some of those situations now. This pattern was not in C++. This pattern of deallocating resources Note in C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition instead of initialization. The drop function in Rust will be familiar to you if you use it already. For the deallocating resources at the end of an item's lifetime, this is sometimes called the resource acquisition is initialization. RA2, RAII, RAII patterns. Called the resource acquisition is initialization. How to pronounce? This pattern has a profound impact on the way Rust code is written. Pattern has a profound impact. It may seem simple right now, but the behavior of a code can be unexpected in more complicated situations. This pattern has a profound impact on Rust. It may seem simple right now, but the behavior of a code can be unexpected in more complicated situations. When we want to have multiple variables use the data people located on the heap. Let's explore some of those here now. Ways variables and data interact move. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer in listing store-2. We can probably guess what this is doing. We can probably guess what this is doing. Bind the value 5 to x. Then make a copy of the value in x and bind it to y. We now have two variables. We can probably guess of what this is doing. Assigning the integer value of a variable x to y. Assigning the integer value of variable x to y. We can probably guess what this is doing. Bind the value 5 to x. Then make a copy of the value in x and bind it to y. We now have two variables, x and y, and both equal 5. We now have two variables, x and y, and both equal 5. We now have two variables. We now have two variables. We now have two variables, x and y. We now have two variables, x and y, and both are equal 5. This is indeed what is happening, because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version. We can probably guess what this is doing. Bind to the value 5 to x, and make a copy of the value in x and bind it to y. We now have two variables, x and y, and both are equal 5. You can probably guess what this is doing by the guesses. 2 and y. This is indeed what is happening, because integers are simple values with known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version. We can probably guess what this is doing. Bind the value 5 to text. Then make a copy of the value in x and bind it to y. We now have two variables, x and y, and both equal 5. This is indeed what is happening, because integers are simple values with a known fixed This is indeed what is happening. Because integers are simple values, these two 5 values are pushed onto the side. Now let's look at the string version. This looks very familiar. So we might assume this looks very similar. This looks very similar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2, but this isn't quite what happens. Take a look at figure 4-1 to see what is happening to string under the covers. Take a look at figure 4-1 to see what is happening to string under the covers. A string is made up of 3 parts, shown on the left, a pointer to the memory that holds the contents of the string, a length and capacity. This group of data is stored on the stack. On the right is the memory on the heap that holds the contents. A string is made up of 3 parts. Take a look at figure 4-1 to see what is happening to string under the covers. Take a look at figure 4-1. A string is made up of 3 parts, shown on the left. A pointer to the memory that holds the contents of the string, a length and capacity. This group of data is stored on the stack. On the right is the memory on the heap. This group of data is stored on the stack. Okay. On the right is the memory on the heap and the group of this data is S1 is stored on the stack. Okay. Memory holds in the contents is on the heap. Representation in memory of a string holding the value hello bound to S1. The value hello bound to S1. The length is how much memory. The length is how much memory in bytes. So 5 bytes. 1, 2, 3, 4, 5. That the string has received from the locator. That the string has received from the locator. Yeah. The difference between length and capacity matters. But not in this context. So for now, it's fine to ignore the capacity. The difference between length and capacity matters, but not in this context. So for now, it's fine to ignore the capacity. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like figure 4-2. Figure 4-2 representation in memory of the variable S2 that has a copy of the pointer, length, and capacity of S1. The representation does not look like a figure 4-3, which is what memory would look like if Rust instead copied and heap data as well. Rust instead copied the heap data as well. If Rust did this, the operation S2 S1 could be very expensive in terms of runtime performance if the data on the heap were large. Makes sense. Earlier, we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for the variable, but figure 4-2 shows how both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. Earlier, we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for the variable. Earlier, we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. The figure 4-2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as a double free error. Double free error, and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 equals S1, Rust considers S1 is no longer valid. Rust considers after the line no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. To ensure memory safety, after the line, the Rust considers S1 is no longer valid. Oh, yes, makes sense. You will get an error like this because Rust prevents you from using the invalidated reference. If you've heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer, length, and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variables instead of calling it a shallow copy. If you've heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer, length, and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable instead of calling it a shallow copy, it's known as a move. Yes. In this example, we would say that S1 was moved into S2. So what actually happens is shown in figure 4-4. That solves our problem with only S2 valid. When it goes out of scope, it alone will free the memory, and we are done. That solves our problem with only S2 is valid. When it goes out of scope, it alone will free the memory, and we are done. In addition, there's a design choice that implied by this. Rust will never automatically create deep copies of your data. In addition, there's a design choice that's implied by this. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of data. In addition, there's a design choice. In addition, there's a design choice. In addition, there's a design choice that's implied by this. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of data. In addition, there's a design choice. There's a design choice that's implied by this. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Deep copy means yes, like that. Oh, there's a design choice that's implied by this. In addition, there's a design choice that's implied by this. Rust will never create deep copies of data. It's moving. At the end of this function, run will call drop on which variables. S1 string from PS2 S2 S3 here S2 is moved, so S2 is moved, deleted. S2 is moved. S1 S3. Determine whether the program will pass a compiler. If it passes, say what will happen when it is executed. If it does not pass, say what kind of compiler error you will get. Determine whether the program will pass a compiler. This program doesn't compile. Let X string from hello. Let X string from hello. Hello. Let X equals to string from hello. So hello, and then hello, and then hello world, and then here error because X is moved. Does not compile. Line here 5. Determine okay, so let u to b equals string from hello, so b is hello, and then b string, b is mutable, so okay, that's the word. B returned, so this returned b, which is expression, so which is represented word, Hey, hello. Let's compile. Hello world. Oh my god. Question 4. String from hello. So hello has 2 and false. B false. Okay, B if B false. What? It's a false. So it doesn't execute. It's ignored. Print S here. So S is hello. Submit please. Yes. No. What? Wait a second. Let's read this again. FB false. This is false. So it will not be executed. What the fuck? String from hello. Wow, why? Ways variables and data interact. Clone. Ways variables and data interact. Clone. If we do want to deeply copy the heap data of the string, if we do want deeply copy the heap data of the string, if we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called a clone. We will discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, you will probably seen them before. Here's an example of the clone method in action. Here's an example of the clone method in action. Here's an example of the clone method in action. Clone. Here's an example of the clone method in location. Clone method in action. Here's an example of the clone method in action. This works just fine and explicitly produces the behavior shown in figure 4-3, where the heap data does get copied. Here's clone method in action. Okay, that's one clone. This works just fine and explicitly produces the behavior shown in figure 4-3, where the heap data gets copied. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It is a visual indicator that something different is going on. Seg only data copy. Seg only data. There's another wrinkle we haven't talked about yet. This code using integers, parts of which was shown in listing 4-2 works and is valid. 5. But this code seems to contradict what we just learned. We don't have a call to clone, but X is still valid and wasn't moved into Y. The reason is that types such as integers that have a known size at compile time are stored entirely on the stack. So copies of the actual values are quick to make. That means there's no reason we would want to prevent x from being valid after we create the variable y. In other words, there's no difference between deep and shallow copying here. So calling clone wouldn't do anything different. From the usual shallow copying, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack. Oh my gosh. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack. Copy trait we can place on the types that are stored on the stack. Trait that we can place on types that are stored on the stack. As integers are, we will talk more about traits in integers are. If a type implements the copy trait, variables that usually do not move, but rather are trivially copied, making them still valid after assignment to another variable. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope and we add a copy annotation to the type, we will get a compile time error. To learn about how to add copy annotation to your type, to implement the trait, see derivable traits in Appendix XC. Rust won't let us annotate a type with copy if the type. Rust won't let us annotate. Rust won't let us annotate a type with copy. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. Okay. Yes. If the type needs something special to happen. If the type needs something special to happen when the value goes out of scope, we add the copy annotation to the type. We'll get a compile time error. To learn about how to add the copy annotation to your type, to implement the trait, see derivable traits. If the type is something special to happen when the value goes out of scope, and we add a copy annotation to the type, we will get a compile time error. Yes, because it's a drop and copy. Because drop can not implement copy, I guess. Okay, so because the reason is because copy it's like just copying, but drop is like it doesn't let copying. So this is related to the stack and heap memory management. And the data that is stored in on heap, that is a drop. It goes out of scope. So when the value or the variable goes out of scope, then that returns the value, and then it will, how to say that, the locator will remove it from the heap. But there's a stack, which is the fixed size, and then always it's like stored on the top of each other. So it's a really quick operator. It's a really fast. So it can copy the data faster. So it just copies the value. But the data on the heap can be super large. And then also it is expensive because you gotta find this memory area when you copy it. So just move. And also when it copies, it drops, then it will allow you to access the wrong data. So it moves. Oh, okay. So the primary values have the copy, and then the memory, the data that is stored, which is stored in memory, heap memory, as a drop trait. Because it does not copy, it's that, so it doesn't have a copy. It's copy trait is like a copying deep copy. Okay. So what types implement the copy trait? You can check documentation for the given type to be sure, but as a general rule, any group of simple scalar values can implement copy, and noting that requires location or is some form of resource can implement copy. Here are some of the types that implement copy. All the integer types such as U32, the Boolean type bool, which values true and false. All the floating point types such as F64. All the integer types such as U32, the Boolean type bool, which values true and false. All the integer types such as U32. All the integer types such as U32, the Boolean type bool which values true and false, a Boolean type, integer type, all the floating point types, the character type, tuples if they only contain types that also implement copy, for example, implements copy, but I32 string does not. Why does the type string not implement the copy trait? Because the string points to the data on the heap. Because the string cannot be shallow copied. Because the char type does not implement copy. Because copy is only implemented for primary types. Why does the type string not implement the copy trait? this. Because a string points to data on the heap. Because a string cannot be shallow copied. Oh, this is about deep copy. It's allowed to shallow copy. Determine whether the program will pass compile. Okay. String from hello or x clone. So x hello or x. Deep copy. So this is a hello world, but hello. Hello. Yes. Why does the type string not implement the copy string? Because a string points the data. A shallow copy would do cause multiple strings to point the same data. Mm. What? The copy is of a shallow copy? Ownership and functions. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. The mechanics of passing a value. The mechanics of passing a value to a function are similar to those who assigning a value to a variable. The mechanics of passing a value. The mechanics of passing a value to a function are similar to those who The mechanics of passing a value to a function are similar to those when assigning a value to a variable. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy. Just as assignment does. Listing 4-3 has an example with some annotations showing where variables go into and out of scope. So the case comes into scope and takes ownership. S's values moves into the function. S's value moves into the function. Here this S value moves into the function. And so it's no longer valid here. X comes into scope. Where X would move into the function. But I32 is copy. So it's okay to still use X afterwards. Here X goes out of scope. Then S. But because S's value was moved, nothing special happens. Here X goes out of scope. Then S, but X goes out of scope, then S. But because S's value was moved, nothing special happens. Oh, yes. Takes ownership, some string comes into scope. Here some string goes out of scope and drop is called. Drop. Hello. The backing memory is freed. It's a copy here. Some integer comes into scope here, some integer goes out of scope, nothing special happens. Okay, just stack. If we try to use S after the call to take ownership, if we tried to use S, if we tried to use S after the call, if we tried to use S, we try to use S after the call to take ownership. Rush to throw a compile time error. If we try to use S after the call to take ownership, try to use S after the call to after the ownership. Rush to throw a compile time error. Yes, these static checks protect us from mistakes. Try adding code to main that uses S and X to see where you can use them and where the ownership rules prevent you from doing so. More service rule is that compiler checks uses to check the codes. Return values and scope. Returning values can also transfer ownership. Listing 4-4 shows an example of a function that returns some value with a similar notation as those in listing 4-3. It gives the ownership moves its return. S2 comes into scope. S2 is moved into text and gives it back. Yeah, it takes the S2 and gives back to S3. Return value into 3. Here S3 goes out of scope and is dropped. Yes. S2 was removed, so nothing happens. S1 goes out of scope and is dropped. Gives ownership will move its return value into the function. It calls it. This function takes a string and returns 1. Function takes a string and returns 1. As a string comes into scope, a string is returned and moves out of the calling function, transferring ownership of return values. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. The ownership of a variable follows the same pattern. The ownership of a variable follows the same pattern every time. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. The ownership of a variable follows the same pattern every time. The ownership of a variable follows the same pattern every time. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes the data on the heap goes out of scope. The ownership of a variable follows the same pattern every time. The ownership of a variable The ownership of a variable follows the same pattern every time. The ownership of a variable follows the same pattern. The ownership of a variable follows the same pattern. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. Taking ownership and then returning ownership with every function is a bit tedious. What if we wanna let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we wanna use it again. In addition to any data resulting from the body of the function that we might wanna return as well. In addition to any data resulting from the body of the function that we might want to return as well. In addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using a tuple. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Determine whether the program will pass a compiler. If it passes, say what will happen when it is executed. Okay, so add the suffix s here, s, okay, and then add the suffix s and s. Add the suffix s here, s is moved, and then s is moved here, and then s is here, s push. Let's push is It's moved here and then returned. Not returned even. It just consumed here, dropped here. Does it compile? It does not compile. Select year 8. Submit. My God. What is the maximum number of times a heap allocation could occur? What is the maximum number of times? What is the maximum number of times? What is the maximum number of times? Maximum number of times. This is like I want to string from hello as a clone. As clone. So it's clone here. That's here. 1. And then print s. Okay, go from 1, 2, 2. And then just 1 and 2. 2. Please, yes. Yes. Program compiles. Yes, I don't understand this B false. So I thought that this is not executed. Oh, wait, let me ask us, please.